All right, in this lab, we're going to have a collision with two cars. We've got a heavier car, which is our news bus, and it has a mass of 49.8 grams. Okay. We also are going to use this lighter car, which has a mass of 29.9 grams. I want to point out that on your lab sheet, it says to convert both of these masses to kilograms. So don't forget to actually divide by 1,000 and convert them to kilograms. At this point, we're going to run the heavier car off of a ramp, and we're always going to start it at the same point. And so we're going to let it go off the ramp, and we'll record where it hits the ground, how far from the ramp it hits the ground. In our second trial, we'll put the lighter car at the bottom of the ramp. Now, when it's at the bottom of the ramp, it will have a velocity of 0 meters per second. And then we'll take the heavier car, starting at the same place, and let it collide with it. All right, when you're doing this lab, we put a place for grams and for kilograms because I want you to actually, although we recorded the mass in grams, for example, the heavier car was 49.8 grams, I need you to actually convert it to kilograms because we need to use kilograms when we're calculating kinetic energy or momentum, when we're actually doing our calculations. So you're going to need to remember that to convert from grams to kilograms, you have to divide by 1,000. Now, the mass of the lighter car, as I recall, was 29.9 grams. And again, you're going to have to divide by 1,000 and get your kilograms. When we, before we did the collision, we ran the heavy car off the ramp, and we found delta x. Well, delta x is the displacement or the distance, right? Or, right, whichever you want to think of it. It's the displacement or the distance, and so our distance for that first car was 96 centimeters. Now, it's 96 centimeters, but I need you to convert it to some number of meters. And so I want you to realize that don't leave it in centimeters, instead convert it to meters. Similarly, after the collision, it went 48 centimeters, right? But again, we want to convert it to some number of meters. Right? Likewise, with the light car, it went 85 centimeters, and you're going to convert that also to some number of meters. Okay? So don't forget to convert these to meters because otherwise your speeds will look awfully fast. Speaking of that, V stands for, as you remember, velocity. But for the purposes of this lab, speed is also a good way of thinking of it. Right? So for our V here is our velocity or our speed. And you're going to find that by dividing by 0.48 seconds. So by 0.40 seconds, sorry, the time that it took it to fall off the table. And so it only takes 0.40 seconds for it to fall from the ramp to the floor. And so that's what you're going to divide by when you're converting your distance to your speed. Now down here, you've got we want to calculate the kinetic energy. And it helps if you remember what the formula for kinetic energy is. Well, the formula for kinetic energy, if you'll recall, is kinetic energy, right, KE, is equal to 1/2 mv squared. And, right? And so we're going to be substituting in for that. Now I'll do this one over here because pretty much I've already done most of the work for the light car. And so for the light car, we know that 1/2 mv squared works out to be 1/2, right, times, and the mass was 0.0299 kilograms, right, times its velocity, which is 0 meters per second, right, 0 meters per second, and squared. Well, 0 squared is just 0, and so this is going to equal 0 joules, right? And so our kinetic energy for this car is simply 0 joules. But don't forget that each time I do these things, I put my formula, I substitute, and I solve, right? So you always want to show your work while you're doing these computations, okay? And you're going to calculate the kinetic energy for the heavy car before the collision, the heavy car after the collision, and the light car after the collision. On the second page, you're going to be adding the two kinetic energies together to get the total kinetic energy. And I would like to point out that when it says total, right, that's just a fancy way of saying add. Okay? Right, so add them together to get the total. Why do we care? Because we want to compare the total kinetic energy after the collision to the total kinetic energy before the collision and express it as a percent. Because if 100% of it were conserved, that would be as if none of the kinetic energy was lost or transferred. Right? And you're going to figure out what percentage you actually get. I've given you the actual equation here, so it's not like you have to discover the equation. The equation is right here, and you're just going to substitute in, and again, show your work here, and then give me an answer as a percentage. Now, in this next section, you're going to be calculating momentum. And I would like you to remember that momentum, which has the symbol P, is equal to m, right, times v, right, mass times velocity, right. For our small car here, right, for our small car, that was equal to 0.0299 kilograms times its velocity, which was 0 meters per second, right, before the collision. And the good thing about that is that it's easy to calculate, and we can say that that was equal to 0, and the units for that were kilograms, meters over seconds. So kilograms, meters per second for the momentum. And again, you're going to calculate the momentum of car 1, you're going to calculate the momentum of car 1 after the collision, you're going to calculate the momentum of car 2 after the collision, and then what you're going to do is add them up so you can find the total momentum before the collision, the total momentum after the collision. So please, again, don't forget that when we say total, we just mean adding, right, to find the sum. Right, so you add them together, you find the sum, and then you can calculate the percentage. And again, I've given you the formula, so you're just going to take your total momenta and right, your total before the collision, your total after the collision, and you're going to put them right here in this equation. Now, why do we do this? Because we want to see which percentage is closer to 100%, right? The closer it is to 100%, the closer it is to being completely conserved, right? And by completely conserved, another way of saying conserved is find the one that stayed constant, right? So when I say that one of them should be conserved, one of them should have stayed constant, right? For the one for the one that was completely conserved, it should have stayed constant. For the one that wasn't conserved, that's the one that actually changed, right? Wasn't conserved means it changed. Well, where did it go? And my suggestion for this is that you actually look at the last page of notes from Monday. You might find that there is good information there.